right, today we're going to talk about water potential and the movement of water. And we've talked about water potential before when we talked about solute concentrations and hypertonic, hypotonic, isotonic. But today we're going to work on how to calculate water potential. So you have a formula sheet. It's in resources if you can't find it. And right here is your formula for water potential. Okay, so all of this stuff right here without pH. Okay, so water potential is basically the potential of water to move into a certain area. And we've talked about that. The lower the water potential is, the more likely the water will be to move in that direction. Sort of like water running is more likely to go towards the lower elevation. Water is going to move towards the lower water potential. And so that means the lower water potential is hypertonic. Okay, so that's good because water always moves to hypertonic. So we're going to look at how to calculate this. So first of all, you have the trident, which is the symbol for water potential. And the water potential, the total water potential for a cell or a solution or a plant or whatever you're talking about is the potential, the pressure potential. So that would be like how much pressure is exerted in that area. So could be like the cell wall, or so the plants have a cell wall and they can increase the water in their vacuole and increase the pressure in the cell, okay, because they don't pop like animal cells do. And then the solute potential. And so that's the total water potential equals pressure potential plus solute potential. Okay, so that's what that means. Now, most of our problems will work. Pressure potential will be zero because atmospheric pressure, like pressure in the atmosphere, that's just zero. And so if you're working with an open container or anything like that, your pressure potential is zero. And we'll look at that in just a second. Now, it says right here, if you want to read here, the water potential will be equal to the solute potential of a solution in an open container because the pressure potential of a solution in an open container is zero. So it actually says that on there if you care to read that during a test, which I don't care to read that during a test. Okay, so basically we're going to focus a lot of time on this right here because solute potential is the one that pressure potential will either be given or it will be zero. Okay, one of the two, given or zero. So this is the one we have to work on. So we're going to look at solute potential. The formula for that is negative I CRT. Okay, so negative I CRT. Okay. And sorry, my document camera seems to be a bit slow today. So then it tells you what all these things stand for. Ionization constant, basically how many parts does a molecule break down into if you put it in water. That's how I think of that. So an ionization constant, 1 for sucrose, because sucrose doesn't break into 2 parts in water. And that's what, so if you put, so basically, if I'm talking about a solution, so I'm going to put my cell into a solution. So like we were talking about when we talked about hypertonic, hypotonic, isotonic, and you have all those lovely pictures, you know, of like, hey, here's a beaker and I dropped a cell into it as if a cell is that size. So this, we'd be looking at like what's in this solution. So if this is a sucrose, I'm going to run off the page. So if this is a sucrose solution, then the ionization number would be 1 because it doesn't break up in water. It doesn't ionize in water. Make sure you always have your negative sign. It's important. And then we have to say, well, then what's the concentration of sucrose in our solution? Okay, so these are all multiplied together. Concentration, I don't know, maybe it's 0.4. That would have to be given to you, by the way. Okay, so then you'd put your concentration on there. And that's the molar concentration, so 0.4 moles or whatever. Okay, and then the R, so this is, okay, so the C is the molar concentration. I is the ionization constant. And R is this is a pressure constant. It's called pressure constant. That's what it's actually called. And it has it's a actual constant, like it has a number, a value. So that's 0.0831 liter bars per mole Kelvin. How did I know that? Because it's written on the sheet right there. Okay. And then we have to say what's the temperature in Kelvin. So this is temp. but it's in Kelvin. Okay, so basically for Kelvin, you just take Celsius. So if it's like, wow, it's 23 degrees Celsius in here. Okay, so I take that and I add 273 to it because that's what the conversion is. That's such a lovely conversion. And so that would be 279.96 Kelvin. Okay, all right. So now I'm just ready to do my little math. That's all I have to do now. So I have to turn on my little calculator. I don't know if you can see my calculator or not. It's pretty bad. So, well, I don't care about that one. 0.4 times 0.0831 times 286 equals, and I have my negative sign. So negative 9.51. And that is the solute potential. Okay, so I've got the solute potential. So it's just doing that little formula. So that's the potential the solute gives to the water potentials, the potential of water to move. Okay, and so then I would say, well, then what's my pressure potential? Well, if this beaker is open, so I'm doing this sucrose that I dropped my cell into. If this beaker is open, then my pressure is 0. So that means then I would say, okay, then plus 0. So then my total, sorry. So then my total water potential would be negative 9.51. And it's that because my pressure potential is 0 in an open container. Now, if we're talking about like two cells that are next to each other, so they're like, two cells that are butted up against each other, and it's like, well, is one going to pass water into the next cell? Or maybe we're talking about a cell that's butted up against like a extracellular fluid. Well, you'd maybe have to consider pressure potential. So it might tell you that the pressure in it is like 4 bars or something like that. And so then you would have to consider that. Oh, by the way, once you cancel out all of your units, and I never do that anymore. I apologize. I probably should. But once you cancel out all your units, this is equal to bars. Okay, so that's what's left whenever you do that. Okay, so units is bars. And feel free to cancel your units all out because it does work. I promise I've done it before, more than once. Okay, so what you're looking for is a value. And once you get your value, then this would be like for the solution. And then we need to calculate for the cell, okay? And so then we'd have to run through all that. Now, honestly, it's very difficult to calculate for a cell because we've got a lot of different stuff in the cell. It's not just sucrose. So typically the water potential for the cell is just given so that you don't have to go through the whole rigmarole of that. And then you're supposed to calculate the water potential of like the solution, and then you'll see which way it goes. So maybe they said, now this cell, maybe the problem said, wow, well, the cell has a water potential of negative 11.4 bars. Too bad you can't read that because it's off the page. And so then it says it's negative 11.4 is the cell. What's going to happen? Well, the water is going to go from here to there because negative 11 is lower than negative 9.5. And so water will leave. Water enters the cell. And so the cell gets bigger. And so what's hypertonic? Oh, well, if it went towards the cell, it means it always goes towards the hypertonic. So that means the cell was hypertonic before all this started. But it's shooting for isotonic. Like eventually you should have them equal. Now, can I figure out what equal is going to be? No, somewhere in between these two. But I don't. That's not necessary for you to try to figure out like at what rate it's going to enter and then what that'll end up being. It's not just like divided by 2. Like you have to actually do a lot more calculations than that. Okay. So basically all you have to do with this is just plug in what they're given. And so you have some practice problems that you're supposed to be doing for your remote work. Make sure that you do those and so that you can practice your water potential. It doesn't really get any harder than this. Like it's pretty straightforward. You just have to plug in ionization. So for salt, ionization is 2, NaCl, and it divides into sodium, chloride, and water. So ionization is 2 for salt. And then concentration, you just, how much is it molar wise? Pressure is a constant, temperatures, whatever the temperature is, the system is in. And then you do it in Kelvin. So you don't want to do it in Celsius. Okay. Hopefully that helps you to figure out how to do water potential problem. And I think that you'll find them very doable. Let me know if you have any questions. Okay. Have a great day. I'll see you soon.